In our last lesson, we reviewed a procedure for analyzing functions based on their intervals. So we would split them up and sort of look at either the function or the first derivative or the second derivative, and we'd analyze those intervals. Today, we're going to be extending that method a little bit further to allow us to classify stationary points, so to determine if those things are a maximum point or a minimum point or neither. Before we get started, let's go ahead and take a deep breath. And let's begin. We're going to begin our learning today with a few definitions. The first definition is one that we should already be comfortable with. The idea of a stationary point. Okay? A stationary point of f of x is a point on a graph where either the derivative is 0 or where the derivative is undefined. We haven't seen very many examples where the derivative is undefined, but I wanted to mention it because it is something that will come up eventually. So for now, we're really going to be focusing on where the derivative is 0. And so that's a stationary point. Okay? Now, stationary points can end up being a few different things, right? The first one of these is that a stationary point can be a relative maximum. It can be a maximum, and what that means is it means that the y value is greater than anything near it. It's what it sounds like, right? It's a point where you're going to have sort of a maximum point where that point is higher than anything nearby. It turns out that we can identify these relative maxima as stationary points where the derivative changes from positive on the left side to negative on the right side. And I want to sort of look at that graphically for a moment. If you think about what it looks like to have a relative maximum, in order to have a maximum, you have to be increasing on the left and then decreasing on the right. In other words, the derivative has to be positive on the left and the derivative has to be negative on the right. Okay, so that's going to end up being the way that we identify and determine whether one of these stationary points is a maximum or a minimum. Okay, so the second definition here is sort of just an analog of the previous one. A stationary point can be a relative minimum if its y value is less than the points that are near it, and we identify these relative minima as the stationary points where, if you think about it for a moment, if you think about any time that we have a minimum, it has to be decreasing to the left and increasing to the right. In other words, the derivative is going to need to change from being negative on the left to being positive on the right. So you can see here that this derivative over here would be less than 0, and then when we cross to the other side of the stationary point, the derivative would be greater than 0. So you can hopefully see how we're gonna sort of use intervals here to recognize, hey, I've got an interval split here, and I'm going to test the derivative on this side, test the derivative on this side, to sort of classify whether this stationary point that we found is a maximum or a minimum. I'd encourage you sort of pause the video for a moment and reread these two definitions. Make sure that it makes sense to you, what I just went through, because this is really going to provide the basis for the rest of what we're doing today, and it's even going to extend into the next few lessons. So this particular slide is really, really important for you to have a good, strong grasp of. All right, so now that we've got a sense for that, let's see if we can apply that knowledge. So in this example, we're going to find and classify the stationary points of a function. So the first thing we need to do is we need to find the stationary points. So to find the stationary points, I need to find the derivative, and then I need to set that derivative equal to 0 or find out where it's undefined. So the derivative for this function, this is just a polynomial, so it should be easy. This is negative 3x squared plus 18x minus 15, and the minus 6 is going to vanish when we take the derivative. This is not ever undefined because there's no division by 0, there's nothing weird happening. So all I need to do is set this equal to 0. So 0 equals negative 3x squared plus 18x minus 15. Looks like I can factor a negative 3 out of that. So that'll give me x squared minus 6x plus 5. And then fortunately, even that factors. I'm going to have x minus 5 and x minus 1. And so clearly, the locations of my two stationary points are x equals 5 and x equals 1. So these things here are the x coordinates of our stationary points. Okay, and again, just to be clear, these are not the stationary points. These are just the x coordinates of the stationary points. So if we want to actually find the points, I'm going to need to plug these back into the original function to find out what their y value is. So we're going to do that really quickly before we classify them. So f of 5 would be, if I plug 5 into these things, it's going to be negative 5 cubed, that's 125, plus 9 times 25, that's 225, minus 15 times 5, that's another 75, and then minus 6. So let's see here. These two things together are negative 200, so this is positive 25 minus 6. It looks like 19 to me. So f of 5 is 19. That means that we know that there's a stationary point at 5, 19. We might not know if that's a max or a min, but we know that that's one of the stationary points. Now for the other one, f of 1, when I plug 1 into the original function, I'm going to get negative 1 plus 9 minus 15 minus 6. So let's see here. These two together will be negative 21, negative 22, and so when we add 9 to that, we're going to wind up with 13. So it looks like this stationary point is located at 1, 13. Okay? So now that I've found these points, right, now that I have these 2 points, I'm going to go through and I need to find out if these things are maxes or mins. And so we're going to do the method that we had yesterday, where we take these numbers and we use them to create intervals. My first interval is going to go from negative infinity all the way to 1. Then I'll go from 1 to 5. And then finally, I'll go from 5 all the way over to infinity. And what I need to do here is I basically need to test the derivative, because I want to know if my function is increasing or decreasing leading into these values, right? So here I'm going to choose 0. I'm going to do f prime of 0. And you may recall from yesterday's lesson that you want to plug that into any of these derivatives. I usually like to go with the factored one because it ends up making it really, really quick. The important part is, like, when you were doing this work on your own, if you divided this negative 3 over, you still have to have the actual original statement of the derivative. So when I test this here, I'm going to have negative 3 times negative 5 times negative 1. That means f prime of 0 is negative 15. Remember, it doesn't actually matter if it's like that it's 15. It only matters that it's positive or negative. Let me give myself a little more room here. And remember what this means. The derivative is negative. So since the derivative is negative, what does that mean about the original function? It means the original function must be decreasing. Now, and like, you had to pause the video and test these other 2 intervals for the derivative and find out whether the function is increasing or decreasing there. So for here, I'll use f prime of 2. Remember, you can use anything between 1 and 5. When I plug 2 into this up here, I'm going to get negative 3 times negative 3 times positive 1. That means f prime of 2 is positive 9. And for this one over here, if I did f prime of 6, I would get negative 3 times 1 times 5. That's negative 15. And so, remember, I can sort of write my statement about each of these as well. Okay, so I now have my 2 stationary points. Then I've got them as full points. And I have this justification here. Between negative infinity and 1, my function is decreasing. Then from 1 to 5, my function is increasing. So what must have happened here at 1? If I changed from decreasing to increasing, then this thing that I had here must have been a relative minimum. So this is a relative minimum, and we can write that. Right? So we can write f of x has a minimum at 1, 13. Similarly, between 1 and 5, my function is increasing, and then right at 5, it changes to being decreasing. So what must have happened here at 5? At 5, we must have had a maximum, right? So that means that f of x has a maximum at 5, 19. And this is the answer to the question. The question was asking us to find and classify the stationary points of the function, and we've now done that. I do want to point out, by the way, that you'll notice that the minimum was the smaller of these y values and the maximum was the larger of the y values. That's not always going to be the case. You can actually have functions where the maximum is lower than a minimum is. And so we really do need to rely on this justification in order to show that. Now, it's important that you know that these relative extrema, and extrema is sort of the plural of extremum. So basically, extreme values, maxima and minima, can only occur at stationary points, but not every stationary point is a relative maximum or minimum. We know that a maximum happens when the derivative changes from positive to negative, and a minimum happens when the derivative changes from negative to positive. But if the derivative changes from negative to negative or from positive to positive, it means we don't have either one of those things. And that's what we're going to see happen in this next example. So for this one, you're asked to show that this function has only one stationary point, and that stationary point is neither a maximum nor a minimum. And so because this is a show problem, we're going to need to show our work, and at the end we're going to want to sort of write out some sort of short justification or reasoning. So your first step here should be taking the derivative and finding the stationary point, and then after that you should set up intervals and test those intervals with the derivative. So if you feel comfortable with what we did on the previous slide, I'd encourage you to pause the video and work through this problem, even if you work through it in stages, checking in with me. So first thing we do is we take the derivative here. G prime of x would be 3x squared plus 18x plus 27. So there's my derivative. Stationary points happen where the derivative is 0 or undefined. This is clearly not going to be undefined anywhere because it's just a polynomial. So I'm going to do 0 equals this thing, 18x plus 27. Looks like I can factor a 3 out of it. Again, so this is x squared plus 6x plus 9. And that actually factors further. This we can factor into being x plus 3 times x plus 3. So it looks like my only stationary point here is going to happen when x is negative 3. And remember, this is only the x coordinate. So just like we did in the previous one, I now want to take that and actually find out what the y coordinate is. Let's find the actual stationary point. G of negative 3, if I plug negative 3 into this, I'm going to get negative 27 plus 81 minus 81 minus 4. Right, so these 81s nicely cancel one another out. These two things that are left are negative 31. So I get g of negative 3 is negative 31, and that means that my stationary point is going to be a negative 3 comma negative 31. So I found the stationary point. Now I need to show that this is not a maximum or a minimum. Okay? So the way that I'm going to do that is by setting up intervals. Right? The only thing I have to break up my domain is negative 3. So I have one interval that goes from negative infinity to negative 3, and one that goes from negative 3 to positive infinity. Okay? And so here I'm gonna test my derivative. I'm gonna do g prime of negative 4. And again, I really like to use this factored one because it really helps me to figure it out faster than plugging back into this thing up here. So this will be 3 times negative 1 times negative 1. That means g prime of negative 4 is positive 3. And I want to write my little statement about what this means down here, but I'm going to figure out the other one first. Here I'm going to do g prime of 0, because I know that's going to be a really easy one. G prime of 0 is going to be 3 times 3 times 3. That means g prime of 0 is 27. So what do we notice about both of these? Hopefully you notice that both of these are positive. So since the derivative is positive, what does that mean about the original function? It means the original function is increasing. And so now that I've got these statements of reasoning, we might say something like, since the derivative does not change sign at the stationary point, it is neither a maximum nor a minimum. And that's effectively all that we need to do for this problem. I might mention really briefly what this looks like. Right? In this problem, what we have is I forgot, was it 3 comma 19? Or negative 3 comma negative 31? I was way off. What we have here is we have a point at negative 3 comma, let's just pretend this is negative 31. Right? You've got a point here, and what happens is my function is increasing. My function is increasing up to here, and then it's leveling off, and then it's going back to increasing again. Right? I've got this point where it levels off, where it's stationary. The graph isn't going up or down anymore, but then it goes back to being increasing. Right? That's what it looks like when we have a stationary point that's neither a maximum nor a minimum. Sometimes it's called a saddle point. So there you go. I have one more example here that's very similar to the previous two, and then after that we're going to look at this problem through a really, really different lens. And those last two problems are going to be quite a bit quicker. But I want to give you a chance to work through one of these entirely on your own if you haven't already taken that opportunity. So the first thing we're going to do is we're going to take the derivative. Right, I need to find where the stationary points are going to be. This derivative is going to be 12x squared minus 4x cubed. All right, So now I'm going to set this equal to 0. Remember, we should also see if it's undefined, but this thing is not undefined anywhere, so we're okay. When I set this equal to 0, I realize I can factor this, so I'm going to do that right away. 4x squared is what I can pull out. When I pull that out, what I'm left with is 3 minus x. Cool, right on. And so now that I have that, I can see that my stationary points here are going to happen either when 4x squared is equal to 0 or when 3 minus x is equal to 0. And both of these things can easily be solved. This one gives me x equals 0. This one gives me x equals 3. Remember, now I want to take these things and I want to plug them back into the original function to find out what the y-coordinates of these points are. Right? So this first one is pretty simple. If I do y of 0, these two terms are just going to get knocked out, and I'm just going to get 3. So one of my stationary points is at 0, 3. We'll find out in a minute if that's a maximum or minimum or saddle point. For 3, let's see here. When I do y of 3, I'm going to get 3 plus 4 times 27 is 108, and then minus 3 cubed, or I'm sorry, 3 to the 4th power, that would be 9 squared, which is 81. So let's see here, these two things are going to come together to give me 111, and 111 minus 81 is going to give me 30. So y of 3 will be 30. Great, so that means my other stationary point is at 3, 30. Great, so I have my stationary points. Now I just need to classify them, right? So I go down here and I set up my intervals. Oh, went a little bit too far. I still want to be able to see that derivative. One of them is going to go from negative infinity to 0. The next I'll go from 0 to 3, and the final one will go from 3 to infinity. I'm going to use my factored version of the derivative right here to test. When I do y prime of negative 1, when I plug this in up there, I'm going to get 4 times positive 1 times 4. This is clearly positive, and so we write, because the derivative is positive, our function is increasing here. Continuing on to the others, here I'm going to test 1. Y of 1 will be 4 times 1 times 3 minus 1 is 2. So this one's actually also positive. And then for my final one, oops, I just realized this should have been y prime. Y prime of, I suppose we could use 4. That would be 4 times 16 times, when I put 4 in up here, this is going to be negative 1. And we can tell that that's going to be negative. And so we write, our slightly different statement there. So now that I have sort of the movement of my function here, I can go through and I can classify these things, right? So what happens here at 0? At 0, our function is increasing and then levels off and then goes back to increasing again, right? So if I'm increasing, leveling off, and going back to increasing, what happened here at 0? Right? This thing was a saddle point, right? So we can sort of see that there's a saddle point at 0, 3. And then over here at 3, at 3, 30, we can see that our function changed from increasing, leveled off, and then went back to decreasing. If we were increasing, leveled off, and went back to decreasing, what does that mean happened here at 3? It means that we had a relative maximum, right? So there's a relative maximum at 3, 30. And this is it. I mean, they asked us to find and classify the stationary points, and we've done that. You notice that I was doing this sort of with the laser pointers we were going along. I think one of the things that's neat is after you've done a diagram like this, you can almost start to get a sense of what this function's going to look like, right? Because we set up this interval, these intervals to be like a number line, like this is where 0 is on the number line and this is where 3 is. That means this is kind of where your y-axis goes, right? And so if you imagine that 0 has a point at 3 and 3 has a point at, no, sorry, that's not to scale up there at 30, you can sort of imagine, all right, so my graph is supposed to be increasing until it levels off, and then it's supposed to be increasing until it levels off, and then it's supposed to be decreasing again. Like all this work that we've done really leads to us being able to have some semblance of what the graph is going to look like. So the final two examples that I have are going to be really, really different from this. They're going to sort of take a lot of the reasoning and the thought that we put into these, and we're going to apply them in a different fashion. So in this next example, I'm giving you a graph. And very specifically, I'm giving you a graph of a derivative, right? So I'm giving you the graph of f prime. And my first question, part A, is can you tell me what the x-coordinates are of any of the stationary points of the original function? Now remember what we've learned in this lesson, right? Where do we find stationary points? We find stationary points where the derivative is 0, right? Now you might be thinking, the derivative is the slope. Right there, the slope is 0. Not quite, because remember, this is the graph of the derivative, right? So if you're finding it like this right here, this is where the derivative of the derivative, this is where the second derivative is 0. I'm not going to talk about that for another day or two, right? For right now, I'm asking where is this graph 0? Where is the derivative 0? And hopefully you're noticing, oh, well, it's 0 like right there and right there. So the answer for part A in this question, is that my stationary points, the x-coordinates, are x is -4 and x is +2. Now part B, I'm asking, okay, can you classify the stationary points? Now again, we didn't actually find points here because I don't have the y-coordinates, but the stationary points that are associated with these, can we classify these things as either maxes or mins? And we actually can, right? If you think about it, our next step in theory would be set up intervals, right? We could set up an interval from -infinity to -4, one that goes from -4 to 2, and finally, one that goes from 2 to infinity, right? Now, what is f prime of -5? Right? Well, look at your graph. If I went over here to -5, remember, this is the graph of f prime. So what is that value right there? Like, looks like it's maybe 3. The most important thing is that it's positive. It's greater than 0. And so because that's greater than 0, it means that my original function, f of x, is increasing. Right? I'd like you to do a similar kind of reasoning on these next two intervals, and then we'll talk about what our conclusion is. Right? What about like f prime of 0? What is the derivative at 0 here? Well, at 0, if I go, I'm going down. This is a negative value. Again, I'm not talking about the slope. I'm talking about the fact that this value is down here at like -3.7 or something. Right? F prime of 0 is negative, and that means that f of x is decreasing. Okay? And then finally, over here, I could do like f prime of 3. 3, the value is clearly positive up here, greater than 0. That means that f of x is increasing. So now that I've figured all of this stuff out, I should be able to go back through and classify these things as maxes or mins, right? First, my function goes from increasing to decreasing. If I change from increasing to decreasing, what must have happened here at -4? It means that there's a maximum at x equals -4. Now, I can't actually get a y-coordinate for it, so all I can say is that that's where it's going to happen. Similarly over here, my function changes from decreasing, levels out, and goes back to increasing. So what must have happened here at 2? There must have been a minimum at x equals 2. And then just like we did before, it means that in theory, we could even sort of picture what this graph was going to look like, right? My graph is going to change from increasing to a maximum, to decreasing to a minimum, and back to increasing again. Now, fun fact, what kind of graph does this look like? Doesn't this look like an x cubed graph? And my derivative looks like an x squared graph? Like, this shouldn't be surprising to us that we can literally see the connections between these graphs and their derivatives and these maxima and minima that we're finding. So I hope that's making sense, and I hope that's clear. We've got one more example that we're going through. All right. So this last example is really just kind of be the reverse of the last one. A function has 3 stationary points at x equals -3, x equals 1, and x equals 4. And the problem goes on to tell us that it has a relative maximum at 1, a minimum at 4, and it has neither of them at -3. And you're being asked now to sketch a potential graph of the derivative on these axes that are provided to the right. Okay. So if you've got any thoughts, I'd encourage you to pause the video and try this one on your own. If you're lost, maybe the hint I would give is, if you're told that these are stationary points, what do you know about the derivative at these stationary points? Don't we know that the derivative has to be 0? So how would I put that on the graph? Couldn't I do that by indicating, oh, my derivative would have to be 0 at -3 and at 1 and at 4? Okay. And then let's go on to use the rest of this information. If we have a maximum at 1, if I have a maximum at 1, for a maximum, the derivative has to change. The derivative must change from what to what? My derivative has to change from positive to negative because I want my original function to change from increasing to decreasing. So this maximum that's happening at 1, the derivative has to change from being positive above the axis to being negative below the axis. Okay? I want you to sort of think for a moment about what that means that you would need to do over at 4. At 4, I'm supposed to have a minimum. Well, for a minimum, the derivative must change from what to what? From negative to positive. Okay, so that means that my derivative is going to need to change from negative before it to positive after it. So we can even sort of like see these kind of coming together here. Right? Now, what does it mean if I have neither happens at negative 3? For neither, the derivative must not change. Must not change sign. So it either has to go from negative to negative, or it has to go from positive to positive. Which is the only one that makes sense here? Should be that it only makes sense for positive to positive, and the reason is there's no way for this thing to get back down to, like I can't go like da-da-da, because I'd have to have another stationary point. So this thing is going to have to come over here, bounce off this axis, and then go back up. So this is my estimate, this is my sense of what this f prime of x function would have to look like in order for all of these statements to be met. So I hope that all makes sense. As always, if you have questions, let me know, and I wish you best of luck as you work through these.